Okay, it's 1 p.m., so I'm going to make a start. Just a reminder to the on-site attendees that, there's no QR code, but there's QR codes on the backs of the different chairs to register your on-site attendance, or you can do it from the IETF agenda online. So please, you will have to do that to ask questions. So please remember to do that. And with that, I will start with the chair slides. Rodney, just chip in as needed. So first of all, welcome to the Quantum Internet Research Group session. As a reminder, this session is being recorded. I'm going to go through the usual IRTF note well. I'm just going to leave this on for a few seconds. And as a usual reminder, the IRTF conducts research, not a standards development organization. So as a reminder, we don't do standards work in the QIRG. Special reminder tips for this meeting. So again, another reminder that the session is being recorded. So as I've already mentioned, for in-person participants, please register through the on-site tool or the QR codes on the back of some of the chairs. And for remote participants, please make sure your audio and video are off unless you're presenting. And with that, let's begin with the chair slides. It seems most things are working, so hopefully this will be actually pretty quick. And hopefully everybody can hear me and I don't drift away too far away from the microphone.
Wojciech, so probably just worth pointing out that we actually have an assigned note taker, just for the record, since we're starting the session.
Oh yes, we have Bruno Reisman who volunteered to take notes for the session. Thanks, Bruno.
Thanks, Bruno.
Yes, so the agenda for today is we start with some administrative stuff and the RG status, and well, hopefully no more hybrid meeting issues. Then Kaushik will present the draft on, it's called use cases, but I think it changed to application scenarios. Then we'll have a presentation from Bart about the Quantum Network Explorer and about programming applications for the quantum internet. This is a research presentation, not a draft presentation. And we'll have some space for a discussion. I put on a point on the discussion point is if there was an online platform like IBM Quantum Experience, but for a quantum network, what would you like to see in one? But otherwise, it's an open floor. We only have an hour, but we don't have a very packed agenda, so we don't need to rush, hopefully. So in terms of status, the principles draft, which we've been working on for the past 2 years, it has been reviewed. Thanks, Marie-José Montpetit. The comments have been addressed on the mailing list, and it's now back for another read for review. It's not going to be presented at this meeting as there's nothing new really other than it's been reviewed. But the other active draft is going to be presented today by Kaushik after I'm done. In terms of other status, we had another seminar in February by Mark Kaplan from VeriCloud. It's available on YouTube if you've missed it. The next one still hasn't been announced, and it's TBD who it will be. And as an interesting other update is the QIRG was mentioned in a publication about what work is on standardization, but I'll make a note. It was mentioned in that document that QIRG does not work on standardization. It was sort of just related work section. But if you're interested in the article, please head over to arXiv and have a look at what standardization efforts are in quantum networks going on in Europe. And with that said, that that's me done for the chair slides. Rodney, do you have anything to add?
Nope, just that I'm sorry I'm not there in person with you all in Vienna. Just travel restrictions are just now getting lifted. But thanks to Wojtek for being there in person, and I'm here with you.
Thanks. Colin, would you like to say something?
Yeah, can you hear me?
Yes.
Yes. Okay, good. I just wanted to check on the principles draft. Is the belief of the authors and the chairs that this addresses all the comments?
Sorry, can you repeat the question?
For the quantum internet principles draft, is the belief of the authors and the chairs that this addresses all of Marie Jose's comments?
Yes, that is my understanding.
Okay, great. Thank you.
Thanks, Colin. Okay, so in that case, first on the agenda is Kaushik. Would you like to? No, we have the Dex pre-shared. Can you click the share pre-shared preloaded slides instead? On their screen. Just next to your share screen, there should be a share preloaded slides, and the one labeled as use cases should be the one you should be sharing.
Like send video, all this. Yeah, can you hear me?
Yes, I can hear you. So if
yeah,
you go
I think
to
I don't
preloaded
see
slides,
like just where is it?
So just next to the button you press to share screen, there's a button that looks like a document that says share preloaded slides.
It's this one. Yeah. Okay.
Brilliant. The floor is yours, Kaushik.
Cool. Thank you, Wojtek. Sorry for that small delay. So it's a small talk. Actually, we haven't made too many updates. Like it was like mostly small changes. That's what we
Can
made.
I ask you, Kaushik?
We tried to take the.
Yeah. Kaushik, can I ask you to speak very clearly and slowly because it's a big room and we might lose out a bit on understanding you. So, thanks.
Okay. Okay. So now is it clear? This one. Okay, so sorry everyone for this small delay. So actually this will not be a very long talk, like it will be like we have made a very small changes. Okay, let's go back to what changes we have made. So first, before going that, let's focus on some of our previous histories. Like, for example, last year in July, we presented our version 7 at IETF113. And then we received some comments, and again in August 20, we uploaded the version 8. And then again we received some more comments from Rodney and John Madsen, and then we addressed those comments on our version 9, and we uploaded it in March 4. And again this year, like on March 6, we uploaded version 10, where we pointed out that there are some more issues in version 9. So that's it. So in a nutshell, like these are the updates. Mostly we added some extra references and everything, except in section 3.2.2. There we added one extra applications on quantum sensors. It is called interferometric telescopes using quantum information. So today I'll just explain what it is in a we'll give you a very brief idea, and that's it. So yeah, so what is that application? It's a quantum sensor application. So what happened, we use interferometric techniques to combine signals from multiple telescopes to obtain measurements with higher resolution. And what we observed that this kind of joint measurement, actually, with the help of this kind of joint measurement, one can get higher resolution compared to if you use the telescopes individually. So the problem is that when we try to do this joint measurement, what we need to do, we need to send those signals like from one telescope to another. And the problem is that if there is a noise in the communication channel, then there could be some kind of phase fluctuation, or your photon might even get lost. To avoid these issues, like what we can do, we can use some quantum, and actually, so this kind of channel loss limits the use of this interferometric techniques, because it can actually reduce the wide area of those telescopes. So what we can do, we can use to increase the spread of those telescopes. What we can do, or to increase the distance between two telescopes, what we can do, we can use intermediate quantum repeaters, and those quantum repeaters can send the photons. That can solve the problem theoretically. Of course, if we want to implement them in practice, there are lots of things needs to be handled. As this is true also almost all the applications we pointed out in this draft. So yeah, that's the only thing we have included here. And with that, we focus on our next step. So this version 10 is relatively stable now. We addressed most of the comments made by Rodney and Joe, and also we provide our replies in the mailing list. And if there are more updates, quick updates, then we can also we are ready to make those updates in our version 10, and we upload a new version. And now the question is, okay, do the chairs think that the draft for the version 10 is ready for the last call in general? So it was we, I think, started 1.5 years ago, but I joined it, I think, last year. So yeah, I think that's it. Thanks.
Thanks, Kaushik. First, are there any questions from either online or on-site attendees? As a reminder to on-site attendees, please still click the raise hand to join the queue. Yes, Rodney?
So speaking, I guess, as an individual reviewer rather than as a co-chair here, let's see. Kaushik, so can you go back? Let's see, what was the date of version 10 here? Version 10 is March 6th. Let's see. And so my round of comments on this was the 13th, right? The latest round.
You mean March 13th, right?
Yeah, March 13th, which Changgang replied to on the 19th, right? Let's see. So he agreed in that email to make some changes to it, but it sounds like we don't yet have complete convergence on a couple of the things I raised in the email. But so your plan is to produce a version 11 sometime soon?
Yeah, so that's the thing. I think okay, so I see that it was on March 13, yeah. So I think we will update after the meeting, we will address all the other comments and then upload another one.
Okay, in that case, it sounds like those comments have to be addressed before we do an RG last call.
Yeah, I think we're getting close. I'm not sure we're quite there, even after these are addressed, because it sounds like there's not yet full agreement on a couple of the issues on it. So I'll try to reply on the mailing list to Chonggang's questions here, and maybe we can reach some convergence on the mailing list.
Cool. Thanks, Rodney.
Okay.
Any other comments before we move on to the next?
Actually, so one more comment or question. For somebody who knows the production RFC editing and production process better than I do, Colin or anyone, this document's going to need, I think, one more good round of wordsmithing and editing, but before it's really ready for final review. Whose responsibility is that? The authors, or the chairs, or does IETF have access to some service to help with wordsmithing and grammar editing and the like?
Colin, would you like to go?
Yeah, the RFC editor does some copy editing at the end of the process after it's been through the last call and the IRSG review. So I think that the responsibility is for the authors to get it into as good a shape as they can, and then the RFC editor will copy edit it.
Okay, good, thanks.
Okay, thanks, Kaushik. Doesn't seem like there's anything else. Bart, would you like to present and share preloaded slides?
Yeah, let's see if I can manage to do that.
Okay, the floor is yours. You've got 20 minutes, Bart.
Okay, thanks. All right, so hello everyone. My name is Bart van der Vecht. I'm a PhD student at QTech in Delft. And yeah, so today I would like to talk briefly about something we've been working on, something called NetQASM. So NetQASM is a low-level instruction set architecture for hybrid quantum classical programs in a quantum internet. So this has been a thing that we've been designing and implementing towards enabling application programming in a quantum internet. So really the idea is that given that you have some kind of physical quantum internet, and given that you maybe have an idea about an application like QKD or blind quantum computation, the question is like, how would you represent this application? How would you program this? And how would you execute this? And so NetQASM is one of the components towards this that we have been designing and implementing, as I said. And later on, I will also explain how NetQASM fits into something called Quantum Network Explorer, or QNE for short. But most of my talk will focus on NetQASM itself. And then again, at the end, I will briefly talk a bit more about this Quantum Network Explorer. So just a quick introduction first. I'm in the Quantum Internet division within QTech. And in this division, we do all kinds of things related to quantum internet. So there are people working on hardware. For example, people working on quantum internet nodes based on nitrogen vacancy centers in diamonds and doing experiments with those. There are people working on simulations of the quantum internet. People thinking, for example, about repeaters, how they should work or how they should be placed in the quantum internet. And then there are people that work on software for controlling and programming such a quantum internet. And so in this last group, this is what I've been involved in. And one of the questions we've asked is, given that you have some physical quantum network or quantum internet, how would you write arbitrary high-level application code and execute it in this quantum internet? And so also specifically, how would you execute and write program code for individual nodes in this quantum internet? And so towards that end, we have designed NetQASM, and I'll explain more about what this is. And around this NetQASM, which is a low-level language, we've also developed an SDK, a software development kit in Python, which allows you to write applications in a more higher level with just standard Python code. We've implemented this NetQASM language and also the Python SDK, and we have also connected this to some of our hardware down in the lab based on NVs in Diamond. And with that, we have kind of showcased the first full software and quantum network stack on hardware, going all the way from high-level Python code to physical quantum networking operations being executed. So first, a little bit of terminology. So the quantum internet, as I'm treating it here, it consists of nodes, and specifically it consists of programmable nodes. So there might be some other nodes in between these nodes, like repeaters, that maybe do not have much control or expressivity, but here we're mainly focused on programmable nodes. So these are these blue circles on the right, and these nodes have some kind of classical processing unit and a quantum processing unit. And in theory, these units can execute arbitrary code, so arbitrary classical code, and also arbitrary quantum code, like quantum gates, but also entanglement generation with other processing nodes. So using these entanglement links in green, the processing nodes are also connected by classical links in black. And applications running on these programmable nodes are in general multipartite protocols, so consisting of multiple nodes jointly performing a certain application or protocol. So you can think of, for example, quantum key distribution, some kind of distributed quantum computing protocol, or maybe blind quantum computation. And so the joint execution of all these nodes we call application in this case, but then each of these nodes individually has to run its own code, has to do its own operations, and for each such node we call this a program. And for the rest of the talk, I will mostly talk about how to write and execute a single node program that is part of a multipartite application. So you could think a bit about what kinds of operations do you have in such a quantum network program. And it's quite interesting because there can be different kinds of operations that can all be interleaved and can also be dependent on each other. So these programs, they might send or receive classical messages to other nodes. They might do entanglement generation with other nodes. They might do some classical processing, or they might want to do local quantum gates or measurements. And so all these kinds of operations can be done in a program, and all these kinds of operations we want to be able to express in our code and also to execute them. So another thing that is part of our context is that we assume each of the nodes in the quantum network, or at least each of the programmable nodes, to implement a network stack. So on the right, we see the layers of the network stack that we assume to be implemented. And so, of course, each of these layers in the network stack has its own responsibilities, and it kind of provides an interface to the higher layers and abstracts away certain details.
Bart, can
yes.
I interrupt for just a second?
Sure.
Your video isn't on at the moment. I don't know if that was what you intended or not, because I know you had yours on earlier.
Oh, right. Yeah. Yeah, let me just...
If you want to have it on for your presentation, and I find it helpful, but... Yep. Okay, good. Thanks.
It should be on now. Yeah, thanks for mentioning. Yeah, so this quantum network stack, if you want to read more about this, here are some references. For example, our very own Wojtek has written something about the network layer, for example, among other things. The link layer protocol has been this paper, but so this talk, again, will be about NetQASM, is about the highest layer in this network stack picture, namely the application layer. Okay, so first, a bit about the execution model on a node in a quantum internet. The way we see it, we use some kind of model that you could call a co-processor model. So within our node, we logically have this separation between an application layer and a component called the quantum processing unit. And so the application layer is responsible for classical processing and also for sending and receiving messages to and from other nodes. And the quantum processing unit is the unit that can do quantum operations, so it is responsible for doing local quantum gates, measurements, but also entanglement generation with other nodes. And these two components, they communicate with each other through NetQASM. And one way to think about these two logically separated components is to think of the application layer as like the main CPU starting this program, and the co-processor or the quantum processing unit as some kind of co-processor to which the CPU dedicates certain parts of the program, namely the quantum parts. And this delegation is done by the application layer sending a block of code. And this block of code we call a NetQASM routine. And this routine consists of instructions in the NetQASM language. And in the next slide, I will give you an example of how this looks like. But the idea is that during execution of a program, the CPU or the application layer is the one that starts the program, and then it will send routines consisting of NetQASM code to this quantum processing unit. The quantum processing unit interprets the instructions, these NetQASM instructions, and acts on them. And it will, at the end of a routine, send back results of this routine. It will send it back to the application layer. Maybe the application layer does some classical computation or communication. So on the bottom right, by the way, you see this example like timeline from left to right. And then the application layer can send more NetQASM routines, maybe based on some classical communication that it did earlier. One interesting thing I want to note is like a difference between this model and model used in quantum computing, so without a networking dimension. So in quantum computing, there is a similar thing going on where often what we call here the application layer would send blocks of quantum code to the quantum processing unit. But then at the end of such a block, all the qubits would just be measured out and they won't stay. In this case, we also have scenarios where we want these qubits to persist in between execution of separate quantum code blocks. Because it could, for example, be that we have a quantum bit in memory, and then we want first to do some classical communication. We maybe want to wait for a classical message coming from another node. And only when we have received that, we can decide, maybe based on this message, what we want to do on this qubit that is still in memory. Okay, so the NetQASM language itself. So I talked about these blocks of code, these routines that are sent to the quantum processing unit and are executed by this unit. So the NetQASM language is quite a low-level language. It's basically an assembly-like language. And if you know a little bit about quantum computing, maybe you might know this language called OpenQASM, which is quite similar. So NetQASM is quite similar to OpenQASM, but there are some more differences that I won't go into much detail right now. But one of the differences is that the addition of instructions related to remote entanglement generation. So those are these create EPR and receive EPR instructions. And these instructions, when they are executed by the quantum processing unit, they are actually kind of sent forward to the network stack that is housed in the node. So the network stack handles requests for remote entanglement generation. So if there is a create EPR instruction in the NetQASM routine, this will be forwarded to the network stack as being a request, and then the network stack handles this request. It will maybe generate a certain number of pairs with another node. Meanwhile, the program code has this wait all instruction, and this wait all actually makes the program block, and it blocks until these qubits or whatever request was sent to the network stack. It will wait until this request has been completed. So for example, it will wait until remote entanglement generation has been generated. And when that has been done, this wait all instruction unblocks and it continues executing these next instructions. So NetQASM is quite low level, as you saw. So NetQASM only handles like the quantum operations, so the quantum gates and also the remote entanglement generation. So what we built around NetQASM is this Python SDK, Python Software Development Kit. And using this software development kit, you can actually write your program code, including also classical processing. So you can just write your classical processing code as Python code. Also classical communication you can express using this Python SDK or Python library. And then all the quantum operations, you also don't have to write it directly in NetQASM. You can also write them in just arbitrary or like in high-level Python code. And then these quantum-related statements in Python code are automatically compiled down to NetQASM routines and sent to the quantum processing unit. So in this way, you can just write your whole program just in Python code. The relevant parts are compiled to NetQASM, and also the communication between application layer and the quantum processing unit is handled kind of under the hood. So you can already use this SDK right now. You can download it as a Python package. You can see the source code and get it. On the final slide, I have some links. You can also already run programs written this way on a simulator. We actually have two simulators that we support. One is called SquidASM. This is based on NetSquid. NetSquid is a quantum network simulator also developed within QTech. It allows, among other things, for the simulation of noise, which is quite nice. Another simulator that we support is Simulacron, which is a bit older but also quite extensive. And so you can also use that. But we also, we don't only want to use this SDK and use NetQASM to run programs on a simulator. We also connected this software to our hardware down in the lab. So on the left, you see it's quite small, but it's just some code that we wrote using this Python SDK. And on the right, you see a picture from a paper we wrote about an experimental demonstration of using our hardware consisting of two nodes. And we kind of controlled these two hardware nodes using various layers in software, and then these highest layers of the software actually used or actually consisted of this Python SDK and NetQASM. So in this way, we show that you can really use this high-level representation of programs and connect it and actually run it with actual hardware. So then I want to mention the Quantum Network Explorer, or QNE abbreviated. So Quantum Network Explorer is a platform that we've launched at the end of last year from QTech. So you see the link there, quantum-network.com. On this website, there is some more general information about quantum networks, what can you do with them. But there's also this thing called an editor. In this editor, you can actually run and simulate some pre-programmed quantum network applications. You can see a nice visualization of these simulations. So for example, you can run a QKD application, and then you see like some qubits being created and entanglements being established. You see which kinds of operations are being done. So this is quite a nice way to kind of get a feel of how quantum network applications work. So as I said, the programs that you can run and visualize right now are pre-programmed, but those programs have actually been programmed using the Python SDK that I mentioned before. And you can actually now also use this Python SDK yourself to write your own applications. And we are working on making it possible to also upload your own written applications to Q&E to see visualizations of the simulation there. And what is, I think, quite exciting is that at some point, hopefully soon-ish in the future, when our physical quantum internet is ready enough, we will connect this to Q&E as well. And when that has happened, you can write your own quantum network applications. And then through this Q&E platform, you can run them on the actual quantum internet hardware. Just some quick things. There is still a lot of things to do and to improve. So yeah, I won't go into too much detail right now. We can maybe discuss it more if you want. But this integration between classical code and quantum code, so the quantum code that is being compiled to NetQASM, it's not quite nice or efficient. Also, it doesn't allow for a lot of optimization ahead of time in the current implementation, at least. So there's some improvements to be made with respect to compilation and optimization. And of course, so this thing that I mentioned, that we still want to connect Q&E to actual hardware. So again, this is not possible yet, but hopefully, well, soon. But no guarantees. So as a conclusion, sorry. So NetQASM is a language, an interface to control nodes, also to express programs for nodes in a quantum network. You can use it to program and run arbitrary applications. You can use a Python SDK to simplify writing code. It's in a more high level. And this SDK is part of this Q&E Quantum Network Explorer platform. You can run programs on various simulators, and in our own lab, we showed that you can also use it to run it on real hardware. And then below you see some links to the Python SDK, so from NetQASM and Q&E, and the link to Q&E itself, and finally just a preprint link of the NetQASM paper. I just want to quickly give thanks to my colleagues who also worked on designing and implementing NetQASM, and also just want to say thank you to you for having me and showing this work. So, and thanks for your attention.
Thanks, Bart. Thanks for the presentation. We have actually an on-site question. Can I remind everybody on the on-site to please say your name first and then ask your question?
Hi, Bart. This is Kiriti. So I have a couple of questions. Are you implicitly assuming that there are two nodes in the network, or are you planning to have multiple nodes in the network? So when you say create ASM pair, is it between me and the other guy, or can you say between me and node X?
Yeah, so I mean between me and node X. So you do need to know some information about the network. So for now, we're kind of just assuming that you know there is this other node with this name, or maybe this node ID or something. And then in your NetQASM code, you would refer to this ID.
Okay, and is it that when you say create ASM pair, you get perfect fidelity, or do you also think about distillation, improving the fidelity of your entanglement?
So you would, in your program code, you would specify a certain minimum fidelity that you would like to have of this EPR pair. But then it's up to the network stack actually to try and produce this pair with this fidelity. And if it does so by using maybe some kind of filtering or distillation, that is up to the network stack, but actually from the application layer, this should be not really visible. The application just wants to have this EPR pair with a certain fidelity, and how it gets created, yeah, it doesn't really care.
Makes sense. Thank you.
Yep, you're welcome.
Rodney, you're next in the queue.
Thanks. Bart, you go back to, I think it's slide 6, page 6, thereabout. had the timeline on it. Yeah, like this. So the timeline there, left to right on the bottom, shows app layer and QPU. Am I right that this is the interaction between the controlling software and the actual quantum device at one node?
Yes, correct.
Okay, what about coordination between nodes? I don't understand the how you handle synchronization and events between nodes on this.
Yeah, so this is actually mostly, it should be handled manually, just in the classical code part of the programs. So if you write two separate programs for two different nodes, you have to make sure yourself that any like send is matched by receive on the other side, for example. So
Okay,
there's no,
yeah, sorry, go ahead.
yeah, there's no like a global entity that kind of handles synchronization of these two nodes. So it's kind of like
running at one node will have its quantum connection, and then it'll to the actual QPU, and then it will have just an ordinary TCP socket or something that connects to the other application in your distributed computation.
yeah, indeed, yeah.
Okay, thanks.
Thanks, Rodney. Shigeya, you're next. We cannot hear you. You must be muted. Oh, you're very sorry. You're very quiet. We cannot hear you. No, still cannot hear you. Are you muted, or is your microphone very quiet? Can the remote people hear Shigeya? Sorry, because sorry, Shigeya, I cannot hear you on site.
I cannot hear them.
We cannot hear your question.
No, can't hear him. Shigeya, while you're trying to resolve that, if your question's straightforward enough, can you just type it in the chat, and then we'll get Bart to answer it. While Shigeya is doing that, Wojtek, you want to roll on to? There's no one else in the queue at the moment, right?
No. So in the meantime, does anybody else have any questions for Bart before, whilst we let Shigeya write his question / wrap up?
All right, so there's Shigeya's question. Are you sending the NetQASM routine every time the app layer calls the QPU? As in, I think, are you sending the code from the app layer to the CPU for every call to the QPU? I guess that's the question.
Yes, we do. So maybe the question is, there's maybe an alternative that you were thinking of, is that all the NetQASM routines were already in some kind of memory on the QPU. So the case here is that these NetQASM routines, the actual contents of them, they might depend on things like values that come up only at runtime. So for example, only at runtime, you might get a classical message from another node saying what you should do. And based on that, you should then create this NetQASM routine. So it's maybe not always possible to already create all your NetQASM routines beforehand. So this is why you only...
Yeah. In the diagram on this same page, there at the left, it says send the NetQASM routine from the app layer to the QPU, and then toward the right, the next pair of arrows, it says the same thing. So what above where it says classical computation communication, there might be some adaptation and some change to the code that's actually going to be downloaded. Is that the model?
Yeah, correct.
Okay. Shigea, does that answer your question? He said thanks. I guess that means yes.
Okay, yeah, but thanks for the question.
Okay. Thanks. It looks like we don't have any more questions. So thanks a lot for your presentation, Bart. It was great. And now we have an open floor session. Kind of don't really have anything scheduled, but this is kind of the time. We have 15 minutes to just throw ideas around. I put one item on the chair slides, but we don't have to actually stick to it. Let me just find it. Oh, we don't have to stick to it. So Bart presented the Quantum Network Explorer. That is an educational platform, but one of the things that, as Bart said, might happen in the future is connecting it to real hardware. So kind of here's a feature request essentially to the QIRG. Yeah. What would you like to see? We don't have to talk about this. Anything else is open floor. And Rodney's already in the queue. So Rodney, would you like to start?
Yeah, actually, this actually sort of goes back to the use case draft. One of the questions that I brought up on the mailing list was the use of the word transmit in the draft. And I want to get away from the use of transmit as much as possible because it really implies to a lot of people that we're encoding some data on a photon and sending it from place to place, and whether or not that photon's actually carrying that important data. Whereas for a lot of our purposes and a lot of the programming model, including what Bart just presented, the network layer service is actually creation of end-to-end entanglement, which then gets used. And sometimes it's used for transmitting or exchanging information from one place to another. Is there another word we can use besides transmit? I feel like it leads people in the wrong direction on this. So I'm not yet prescribing. I'm asking for other discussion what people think about that choice of word.
Curity, is your hand raised for this question or for our next one? No, okay. Yeah, so does anybody have anything to answer to Rodney's question? Somebody in the chat just said +1 entanglement. Robin Wilson said +1 entanglement means that we need new language, but does not have a suggestion. I mean, we generally use generate entanglement, which actually I also don't like, to be honest, because what you're really doing is you're creating entanglement. You're causing 2 qubits at 2 separate nodes to become entangled, which I guess can be called generating entanglement, but it kind of implies you're creating something from nothing, which is not really the case. But yeah, sometimes you do transmit data when you're teleporting a qubit. You do transmit the data.
Yeah, so I think I maybe didn't say it as clearly. So the use cases that they are talking about, at least the paragraph I was looking at a few minutes ago, moving data from one node to another, but that can be done either by encoding it on something and transmitting it, or by teleporting it. And so I think we need a word that says, we don't care what mechanism you use for moving the data from one place to another, but for this particular application, the data gets moved from A to B, and then maybe from B to A after you're done with some computation or not. But so either transmit or teleport, I think, carries baggage that's a little more specific than what we want. Dave's suggestion in the chat there says state synchronization. But I'm not sure. State synchronization is one of the things you can do with entanglement, for example, but that's still not quite getting the move data from point A to point B via some mechanism that might or might not be transmit.
Yeah. Okay. I suggest people threw a suggestion in the chat, and I'll let Curity it's because we only have 10 minutes, so I need to try to get through as much as we can. Kiriti, and a reminder, can you say your name when you ask your question?
You've said it twice, but Kiriti here. It's an open question. Is there research going on distributed computing, distributed quantum computing, and things like if I need 100 qubits for a certain computation on a single node, but if I now can distribute it over 2 nodes or 5 nodes, how much do I need per node? So maybe I still need more than 100 qubits to do the computation, but on any given node I only need 10. So I'm actually in a better place because I can't build a computer with 100 nodes. 100 qubits. That kind of research where the ability to actually entangle between nodes reduces the per node requirement of how many qubits you need. Does that make any sense?
It makes perfect sense to me, and I do have an answer, but I want to see if somebody else wants to chip in before I do. So I might as well say, yes, there is research going into distributed quantum computing. In fact, the department I work at is called Quantum Internet and Network Computing, where the network computing is specifically to address distributed computing. This is ongoing work in progress. A very crucial difference between quantum internet and what we call network computing or distributed quantum computing is, same as in classical computing. You can globally orchestrate if you're distributing computing. So at this stage, it's currently very different lines of research, and a big challenge in distributed quantum computing that I see and I hear from colleagues is that it's not immediately obvious how one can distribute a quantum computation over multiple nodes. It's not exactly a trivial thing because it's a big question as to what is the resource through which you distribute. Do you just parallelize an effort? And if you parallelize, is it actually giving you a gain? Or if you don't parallelize and you instead create entangled pairs between all of your 50 nodes, how do you actually use that at that point? So all those questions are highly non-trivial. And when I ask theorists about the status, they kind of don't have a coherent answer, or at least none that I have heard of. So yes, it's ongoing work. If you Google, you'll find quite a few things going on. I think I'd recommend looking up papers from a researcher called Simon Benjamin. So yeah.
Okay, thank you.
Diego, would you like to go up next?
Was not sure if I was on time. Just a couple of comments. One is regarding what you were mentioning here about the distributed quantum computing and the internet computing. This is something that connects as well with some reflection I had looking at the use case document. Because, well, and it's totally normal, but it's a situation in which we seem to be right now more analyzing cases for for quantum communications rather than for the internet. Quantum internet. For example, I don't know, whatever the case is interesting that the nodes are able to communicate, but then the internet is precisely about how these individual islands of communicating stuff can communicate it to one another using a uniform mechanism, whatever it is. I mean, right now in the internet, we have IP and we have the transfer protocols and that's it. That step is something that, well, it's still a challenge. I'm not saying that there is a solution, but this is something that probably is a twist that we should have in the use case document. This is something I was taking note because I had to elaborate. This is something that came to my mind when looking the. The second thing is regarding what Bart was presenting. In a certain moment, I saw the sort of the transport layer overstruck that. And precisely what this language is advocating is precisely for using a transport layer.
Okay.
What I mean is that the language, the QASM, assume that you don't care about, you have an identifier that connects you to the other node, and you don't care whether you're using teleportation, transmission, or whatever characteristic, whatever. And this is, in my view, that's precisely what the transport layer provides. So it is not that the QSM eliminates the need for the transport layer is that precisely it requires the use of a transport layer to support the computational model.
Yes. I actually do have a comment about that because it's my fault. It's crossed out in there. It's not so much that there is no need for a transport layer. It's more an indication that we don't have one. As in, it was
okay.
suggested, but we just have never got around to
okay,
thinking
okay.
about what to actually do in it. The reason it originally said qubit teleportation, but a lot of quantum network applications don't need to teleport data. They actually just use entangled pairs straight away as their resource. So, but no, there might be a need in the future. It's just not well defined. So actually, that might be something to think about in QIRG. Is to what could be a transport layer, because it's definitely not a trivial translation of the classical transport layer.
No, sure.
But as you pointed out, there might be some need for such a layer.
Or we should start thinking about quantum sockets or whatever. That's yeah. But while you were talking, I was trying to figure out whether a qubit teleportation could be one kind of UDP, and other mechanisms could be like TCP. I don't know. But just fantasizing, not that I'm saying anything. Just to start thinking about it. Thank you.
Right. Thanks. We have 5 minutes as a reminder. So Rodney, are you still again in the queue, or did you just never put your hand down? Okay. There is actually a question on the chat. Pre-canned there. I have seen from Bruno. I've seen pre-canned demos on Q&E, but is it also possible? Will also be possible to submit my own NetQASM programs for execution in Q&E? Yes, and Bart said yes. It's work in progress. Okay. Anybody else have any questions? We have 4 minutes, so if not, we will just wrap up. Rodney?
I'll just echo what I just actually wrote in the chat. The discussion about transport protocol is actually a good one, and that's an area where it would be really nice to get input from my group and from the Delft group and from other groups, and sort of collaboratively figure out what a transport protocol ought to be. And so maybe QIRG would be a good place to actually do that work. But that would require somebody actually stepping up and planning to actually lead and organize such a thing. So all the participants here should think about that. What do we want QIRG to do next, and would you be willing to lead such an effort?
Yeah, it'll be a great unit of work for QIRG. I've got a bunch of thoughts, but it's not something I or QTech, I think, will be working directly on anytime soon. So I think it's something great to discuss if somebody else wants to pick this up. Okay, without any more questions, I will then close the session and thank all the attendees, both online and remote, and thank our speakers and people who ask questions. So thank you, everybody.
Thanks all. Bruno, thanks for doing the notes.
Oh yeah, thanks, Bruno.
Stay safe, everybody. Looking forward to seeing you all in person sometime soon.